Okay, hi everybody. So what is the Taylor series? Taylor series centered at a point. Okay, so part A, using, or I guess I would say, if we can evaluate the function at a point. Let's call this point A, and evaluate its derivatives at that point, A, then we can create a power series. This means we're going to create a new function, a power series function that sends, so instead of x, well, it sends x to what? An infinite sum. And we're going to go from n equals 0 because it's a power series. What are the powers? X minus a to the n. So note that there is a variable here because we are creating a function. The power series function is a Taylor series. And so we do have a variable. But what are these coefficients? So these coefficients we're actually going to have to plug in at the point A, take the nth derivative, and evaluate it at A. So there might be an x there in the nth derivative at first, but we'd plug in at A and get a number, and then divide by n factorial. And this will be a number, and this has a variable. Okay. So, you might think of these as the a sub n's in some x to the n. That would be centered at 0, or the a sub n times x minus a to the n. But whatever, they're just numbers. They're coefficients. Okay. Great. Now, part B. Compute the Taylor series of this function at the point 2. Okay. So we have a function, let's call it little f, and it sends x to 1 plus x square root. So we already can evaluate this at a lot of numbers, but what if we wanted to put x in the complex numbers? Well, at the point 2, we can evaluate this function. We can evaluate all its derivatives at the point 2. So we could take the point 2 here and hope to extend it into the complex numbers, and be able to plug in any point in this disk. Okay? And so we will use a Taylor series to do that. Okay, so first of all, what are the derivatives? So first, the square root of x is easier, so let's just do the whole thing. So what's f prime? F prime of x is, so this is f of x. Well, here, this is going to get too cluttered, so let me organize. F of x is square root of 1 plus x. F prime of x is 1/2, 1 over 2 square root of 1 plus x. Can you take the derivative of this function? The chain rule will give a 1, so the chain rule doesn't really do anything here. Okay, so now this is x to the negative 1/2. Okay, so now I have to think. X to the negative 1/2 becomes 3/2. Okay, so I'm going to get there already was a 1/2, but now there's going to be a negative 1/2. And then 1 plus x to the 3/2. Negative 3/2. Okay, and then f triple prime of x equals And so what's that going to be? Well, we're going to get now a negative 3 halves coming down into x to the negative 5 halves. So I guess it's going to be 1/2. And we could keep going, but let's stop at 3 derivatives. Hopefully I did this right. Now we're going to evaluate at x equals 2. So f of 2 is square root of 3. F prime of 2 is f double prime of 2 is, I have to plug in a 2, f triple prime of 2 is some number. And now what we're going to do is we're going to use these numbers after dividing by some factorials and create a power series. Namely, what power series? It's going to take the variable x and send it to the square root of 3 plus some amount of x minus 2 plus some amount of x minus 2 squared plus some amount of x minus 2 to the third plus dot dot dot. And what amounts? Well, 1 over 2 root 3. That is the coefficient of x minus 2 to the 1. Here is the x minus 2 to the 0 term. And let's see, the second, so I'm using this formula. The nth derivative evaluated at a divided by n factorial, x minus a to the n, where a has been chosen to be equal to 2. And I'm really only going to go up to the degree 3 term. Now here I'll need a 2 factorial downstairs, so negative 1/4, 3 to the negative 3 halves, and then divide actually by another 2 factorial. And over here I get 3/8. But then I have to divide by 3 factorial. So we could cancel that 3 and that 3 and get a 2, but anyway, so there we have it. This is the Taylor series for the function at 2, or centered at 2. Obviously I didn't complete it, but you could keep going. Okay. And you know, this pattern is interesting, the pattern in the coefficients, and if you figured out the pattern, you could actually find out what is the radius of convergence by using the ratio test perhaps, and seeing if you could figure out what this limit is, and if it's less than 1. Okay. That's all.